Thanks a lot for the invitation. I've learned a lot about systems today, so I guess you will learn a little bit about 3D problems. I'm not going to present many equations in detail, but more talk about what the difficulties are if you want to couple several of them, different types of equations together. I've changed the title a little bit and called it How to Fix Incompatibilities in Multiphysics Simulation with a Coupling Library. And we will see in the beginning what these incompatibilities might be and why we do not simply avoid that and take the easy way without incompatibilities. So our target is, as already mentioned, we have different parts of a model. It could be a fluid simulation, it could be heat transport, it could be an elastic structure deforming, but it could also be equations in a different dimensionality, like a 1D structure. For example, in the human blood system, you might model smaller blood vessels just as 1D structures and just the larger ones as 3D. So the question is, could that simulating such a system be just fun instead of hard work and consuming a lot of compute power? And can we do this in a plug-and-play way instead of doing a lot of recoding, new code development, and developing a lot of new solver numerics as well? As for us, different from Bosch, numerics is not just a book, but it's really hard work which we have to invent, which we have to invest in coupling here. Can we do this based on our own previous work or on someone else's work, which would be even better and easier? And on supercomputers, as we want to go beyond what the Modelica CFD component can do, beyond just a couple of thousands of cells, but just to like 10 to the 9 elements in a PDE simulation. And this means we need to use parallel solvers, obviously, and also the coupling of these parallel solvers should account for that and not generate a bottleneck which dramatically slows down everything. So what kind of incompatibilities are we talking about? So the first one is, of course, we have different physics. I mentioned fluid structures, heat transport, could also be acoustic wave propagation and many other things. We could have, or we in general have non-conforming meshes, because our idea is we take any solver doing one of the physics that we want to bring together, a good one, of course, scalable one, fast one, accurate one, and then we glue them together. So typically they don't care about each other's meshes, but they just take their own mesh generator and they don't match at the places where they physically come in touch with each other. They might also have different time-stepping methods, high order or low order, explicit, implicit. The problems might be multi-scale in space and in time. We might have different dimensionalities. I mentioned these 3D, 1D blood flow example. Could also be a 2D fracture in a 3D structure or things like that. The different solvers run all in parallel, and they usually define their own domain partitioning, so that doesn't match and also doesn't care the same as the mesh about what the other side does. And they might have different programming language. So one might be an old engineering code in Fortran, and the other one a Java code or a MATLAB code or a C++ code. So why do we not avoid that? Different physics, well, this is inherent to the scenario. We more and more do not only want to simulate the flow around an aircraft, for example, but also the acoustic wave propagation and the bending of the wings of the aircraft. As an example. Non-conforming meshes, we could, with a lot of work, maybe avoid that, but sometimes this is also an advantage if you have a complicated geometry or if we have boundary layers in turbulent flow, then we do not want to force the fluid mesh to do the same as the structure mesh, for example. So then it would be really good and not just a problem if we would have non-conforming meshes. Different time stepping, also something which is quite obvious. If you're doing numerics, also for ODEs, you might have a stiff system and a non-stiff system and want to couple them together. So why should you do implicit time stepping for everything? You might take the non-stiff system and simulate this with a Runge-Kutta scheme, fourth order, and only the stiff system with an implicit whatever, Euler, for example. And then you want to bring this together and not lose accuracy because of the coupling. Different dimensionality is sometimes a necessary simplification. So I mentioned this blood circulation system of a human being. It's simply not possible to do this fully in 3D up to the smallest blood vessels. You have to simplify somewhere, because even our supercomputers would not be capable to simulate this as a monolithic 3D system. Independent domain partitioning, well, if we want to be flexible and if we want to be able to use any code, this is just what we have to cope with. The same holds for different programming languages. So if you do not want any restrictions in what code you can use, for example, do not want to say, well, I cannot use this nice finite element structure solver because it is in Fortran and everything we do is in C++, then we have to find a solution here. So what we have as a solution, we have developed for many years now. Initially, we started this under a different name back in 2003, trying to couple different codes in an as black box and as plug-and-play manner as possible. And the current product is called Precise, Coupling Library for Partitioned Multiphysics Simulations. It's open source, so you can go to precise.org and download everything. And what you can do with this, you can take any solver. Let's start on the upper left. A fluid solver, there are mentioned some examples which we already have coupled to something else. And then you write a small adapter code which calls library functions, and that is the connection to the other solver. So while writing this code, you do not have to decide yet what you use on the other side. So if you go to the right, there's a structure solver, and you could choose from these whatever you would like to do. And this also has this adapter code, and the green part is the precise function calls. You can also do this for a commercial code where you typically have to write some kind of wrapper rather than an adapter, or for your in-house code. And you can then, if you have an in-house code where you really maybe modify your main function, you can use different application programming interfaces, C++, Python, C, or Fortran. So what is these green parts? What do they do for you? They first of all establish a communication link between two solvers. So you take your usual partitioning, start both programs in parallel, and via these adapters they will connect and also find out which ranks, which processes of which solver have to talk to which of the other parts. So this is, we will see a picture later on where this shows that this is done without a central bottleneck. You can map data. This also works more or less automatically. You just give your point clouds at the surface. Let's say we stick to our general example, fluid structure interactions. You have a surface between the fluid and the structure, and you only need to give data points and values at this interface and the data points of the other solver, and then this mapping is done also automatically for you. We have implemented coupling schemes. We'll see this on one of the first slides, what this means. This means you solve a fixed point equation at the interface, and you do this in an iterative process. It doesn't work right out of the box in a naive way, so you have to accelerate this. And we are now just implementing some time interpolation, which enables you to achieve more than just first order accuracy in time. So I will show these nice pictures only shortly. This only is supposed to show you that there's more than one PhD student working on this. So it's a larger group, and the one on the lower right is currently the main developer, Benjamin Ueckermann, who is now in Eindhoven. So this is also a slide just showing you a number. We have a lot of users here. One prospective user is here in Lund, Philip. And you see also that we have users from industry, from academia, from different fields, engineering, medicine. So you can use this in very different fields. It's not restricted to one specific application. And you can also see that at least people visit us at GitHub and have a look at the tool. So coupling. This is the one numeric slide that I will show. Coupling could be so easy. You just run, let's say, a fluid step. then you calculate some forces, and then you run a time step of the structure solver, and then you have new displacements and go back. Unfortunately, this is unstable, doesn't work, not only for fluid structure interactions, but also for many other examples. So you have to do something, and what you do is you formulate your interface problem as a fixed point equation. And I think we all know that if you have a fixed point equation, you can do a fixed point iteration, but it's never going to converge, except from rare cases. So you have to accelerate this a little bit, and that's what you see at the bottom. The IF is the fixed point operator, so you first do a kind of prediction, fixed point iteration, and then you accelerate this in a Newton-like step. So you see you have here a J inverse. This is in Jacobian matrix, and R is the residual of the fixed point problem. So how is this done? Computing a Jacobian matrix is something which a computer scientist who wants to run large-scale problems should never do. Why? Because it's not linear complexity in the number of unknowns, but at least just storing this matrix would also already be n square. So we'll never do this, but we try to estimate or approximate the action of this inverse Jacobian, and we do this by collecting difference data, input-output data of our fixed point operator during the Newton iterations. So iterations that we do anyway give us kind of data, and data equals information here. If we first do a fixed point step here, and from that we can reconstruct the inverse Jacobian matrix. So these are complicated formulas, but that's the simple idea. Basically, it's like approximating a derivative with a difference quotient. That's what we all can do. And this is the generalized form in a multidimensional setting where you have thousands or millions of data at a coupling interface. And you see there's a lot of matrices. So this means if you have these formulas, you develop an algorithm which first of all is parallel and second never stores a matrix, but only low-rank approximations such that we still have linear complexity and scalability. So I would like to show you a couple of examples, and each of these examples addresses one or two of these incompatibilities which I've shown you in the beginning, such that you get an idea how this works. First example, heart valve simulation. Second example is an academic example, conjugate heat transfer in a very simple problem. Then I will show you an example where we did some experiments with load balancing, which is not trivial. You have two codes, both running in parallel. How do you ensure that they both take the same time between iterations or from one time step to the next? So the usual approach, I just assign some weights to some finite elements, doesn't work because they're different implementations, different languages, different compilers, different numbers of iterations, so you have no idea how these relative weights should be chosen. Then I will show you a short bit about intercode communication, then a 3D, 2D example, fracture opening in a porous medium, and finally, example again from medical sciences, fluid structure interaction for the human aorta. Well, different spatial resolution, why is that a problem? So first of all, this is the setup. This has been done by one of my PhD students. So he brought this problem from South Africa when he came into our group and tried to couple this heart valve fluid interaction with our tool. So the fluid mesh is very fine because of the complex fluid, but the heart valve itself is rather coarse. This also prevents a little bit instabilities. So what he did first, he took the simplest components of the coupling and decided to have just a nearest neighbor projection method for the mapping. He mapped data from the coarse structure to the fine fluid mesh, and on the right you see a visualization of what happened, which is quite obvious, but you might not have it in mind. Then you get such a not very nice stepwise solution on the fluid mesh. So that means just projection is not sufficient. You have to provide more sophisticated, more data mapping methods. And what we do here is, for example, if you don't want to calculate an interface triangulation, you just have data points. You don't know how they are connected to triangles or quads or whatever. Then you can do radial basis functions. We've actually seen them already in the normal distribution. So you have just these Gaussian kernels, and you take them as basis functions and try to interpolate your function. You have two problems there. The first is if these Gaussians are too small, then you get an oscillating interpolant, which is not nice because if you evaluate it between grid points, it's really ugly and inaccurate. If they are too wide, the condition of the system you have to use is awful, and you never get done with it, or your solver doesn't converge at all. So we did some things about that. The numerical thing is you do some rescaling. You take Gaussians which are not too wide, and then you just divide them by the interpolant of 1, and you kind of cancel out these oscillations, which you find in both. The second thing, the lower part of the slide shows you what you have to do in the implementation. We, of course, also don't write all numerics on our own. We used PDE to solve this system of equations for the interpolation. And if you do this in the wrong way and don't tell PDE in advance, this exactly is the sparsity pattern of my matrix that is to be solved, then the runtime takes just forever just to assemble the matrix. So you also have to do something here, and the thing which you have to do here is compare grid points of both sides and tell which are connected by a Gaussian basis function, so which points are important for which points of the other mesh. And this, again, should be done in linear complexity, so we did some work here. I don't tell you the details, but you see we got from these ugly, huge blue bars to the yellow little things that you can hardly see. So we reduced the runtime to almost 0 for doing that. So this was kind of the first one was kind of a real world example. The next one, this is very academic. And we have a fluid which we simulate with our favorite fluid solver. And at some part of the bottom of this channel, we've attached a structure, and we calculate the heat transfer between the fluid and the structure. So this is not a deforming structure, but only heat transfer. And there we have used different time steppings. And what happens usually if you use different time stepping methods, different order, or just different step sizes, is what you see here in the middle. One solver just extrapolates its solution of one time step until the next in a constant way, and then you give that to the other solver when it asks for data at that point in time. And this is very obvious and also known from numerical splitting methods for ODEs, that this is only first order no matter what you do on either of the sides. So you can do two Runge-Kutta-4 methods. This is always going to be only first order if you couple it this way. And you can do better. You can look at a whole window of time steps, and then you can do interpolation with a suitable order and give the data of this interpolated function in time to the other solver. And then you get the order that you expect. You get the lowest order which you have in either of the solvers. And yeah, this is just a little sketch that we actually did, some convergence experiments. And yeah, the method did what we expected it to do. So you get second order if you think you get second order, and fourth order if you couple two fourth order schemes. So this was all kind of numerical. The next one is about load balancing. So this is maybe an even more academic example. We have a Gaussian pulse which is spreading. So it could be a pressure pulse or density pulse. And what we do, we take an in-house code of one of our cooperation partners in Siegen, which is very nice because it's a high order code. So you can vary the spatial resolution, you can vary the order, and with that you can completely mess up your load balancing. You just take different orders and different resolutions in two parts of the domain, which is an inner rectangle, which you can see here at the upper part, and an outer domain. And then you have no idea how you should balance this. If you do this in a heuristic way, you get some load balancing, which is kind of working but not optimal. And we did this based on a performance model. So here's again some data and some learning. So you set up a model, you decide which bases you take with a kind of binary search approach, and then you minimize an objective function, which is the runtime of the slowest component. And then you can get from runtimes indicated by the black bars to the green bars, so you reduce your runtime from your heuristic best that I could do based on my experience to what this automatic model does. So this requires some offline phase where you run some simulations for both solvers, generate data, then you do your modeling, and then you do the optimization. The optimization itself is very simple. It's a very restricted, discrete space, so you can even do this in a brute force way. So this is not the difficulty here. Now they run with approximately equal runtime. So you can run them in parallel. So the question is what happens in between at the synchronization when they communicate. So at the top, you see what some commercial solvers or some commercial coupling tools still, some of them do. You just take two parallel codes and all their processes send their data to one server process, one server rank, and then it's distributed again to the other side. So if you imagine you use the world's largest supercomputers with a few million cores, and a million cores send their data to one central instance and back. This doesn't work, and we showed that it even didn't work for 32 nodes at the supercomputer in Munich. So it's really a very low number of very low amount of parallelism that you can achieve with this approach. What you have to do, you really have to make these two sides talk to each other, send their data in a hierarchical process, again, to still achieve linear complexity, and then define communicators, communication connections in a point-to-point way, and totally remove the central instance. So this is also why we are a library and not follow a client-server approach. Yeah, and you can do this. The interesting part is the light blue line. This is what we had before when we still had the server-based approach. So we had some parallelism, but it wasn't great. And you see that already at 128 cores, you should have a decrease within a steepness of 1, and you see that this already flattens out here. So it really doesn't work. Yeah. So this is one more recent example, which we did with an engineering group in Stuttgart, who are coupling porous media flow simulations with an opening of a fracture. So you have a fracture which is modeled as a lower dimensional structure. So of course it has an opening width, but it's as small, it's that small that you assume that this is computationally it's a lower dimensional manifold in your 3D domain. So here's some equations, which I won't explain. So you have a Poiseuille flow in the structure, in the fracture, which means you reduce your Navier-Stokes equations to 2 dimensions, and you only have a pressure and an opening width, and you have a flow in this 2-dimensional direction. And the other part is the 3D equation, poroelastic equation for this porous structure around the fracture. And you have some coupling conditions. That is what is indicated here in yellow and in green. This is the variables that have to be equal on both sides. And that defines your interface fixed point equation. Again, you have to do strong coupling. You cannot just send data once per time step, but you have to iterate to make this work in a stable way. And yeah, we've already generated some first images. It's hard to see much, so you see some fractures opening here in this 3D structure. And again, we have a fine structure mesh now versus a very coarse, a fine fracture mesh. So in this fracture, you have to need a high resolution, and you can have a very coarse structure mesh, which is for them the main advantage to apply this partitioned approach. Yeah. You could also fully 3D couple free flow, not just in a fracture, but you imagine you have a river and a river bed and you want to couple the flow, or you might even have a flow which is not parallel to the porous medium, and you can also couple this. The problem here is that there's not really a good iterative solver for the whole system. So if you write this as one big system of equations, it's very ill-conditioned and it's very hard to come up with a good solver. So we said, let's give it a try and see if you use the best solvers they have for the flow and for the porous medium, for the Darcy equations, and couple them together with these quasi-Newton schemes, which I showed you in the beginning. Does it work? And it actually does. It works a little worse than for flexible structures and flow, but it does work with like 30 iterations per time step. So this is not very satisfactory yet, but you get some results. The actual research task here is to enhance the boundary conditions, so to make them physically correct. So they are going to change several times throughout the next 2 years probably, what they define as the best boundary conditions. So this means they also need a flexible approach where you can just say, well, let's change the boundary conditions, let's change the interface equations. And they don't want to write a new solver every time. They do this, and that's why this modular approach is so nice here. Last example, human aorta. Here, again, a guest from Barcelona tried a different kind of coupling. He only coupled the pressure in a strong way and the velocities in a weak sense between this elastic wall of the aorta and the flow inside. He used these quasi-Newton schemes and different time-stepping methods, and the results looked as they should. So they were very satisfied with the results, and this also scales up to, I think they're now at something like 16,000 cores. So you can really run this in parallel. And it worked, again, without having to rewrite your own iterative solver and your own parallelization for this problem. Finally, where can you get this? You can already get this. You can download Precise from precise.org. You can couple your own solver with any other. So if you look at the web page, you will also see that there's a lot of adapters coming with the coupling library. So if you find a solver which already has an adapter, you can really download the whole package there. It's easy to couple. You only have to add a few lines of code, call the mapping, call the sending of data, advance, which means execute the other solver, and then you're ready to go. So if it's an easy code, it can be done in a couple of days. It's fully parallel. It has an implicit coupling accelerated, and you can also couple more than 2 solvers. So if you have 3 fields, you can also do that. I didn't have a good example here. We only have academic ones, so they were not. I think we had enough academic examples here. So with that, I'm done with my talk and looking forward to your questions.